Example 5. The wave function for a harmonic oscillator, i.e. a vibrating chemical bond, can be written as psi equals a e to the negative x squared, where x is the distance from the equilibrium position and a is a constant. Part of the process of working out kinetic energy of the moving atom deals with derivatives of this particular function. So here, part A, we want to identify the independent and dependent variables for this equation. So here, I was told that a is a constant, and I also know that e is a number. Since x is the distance from the equilibrium position, x must be my independent variable. So my independent variable is x, and my dependent variable is this funny looking thing on the left, which is psi. It's a Greek letter used when we talk about the wave equation. We now want to find the first derivative of this function. So when I take the derivative, I have to remember what my independent variable is. My independent variable here is x. So I'm looking at what's happening in terms of x. So when I think about the first derivative of this function, one of the things I notice is that I have e to the negative x squared. So that's going to be a chain rule because I have this negative x squared in the power. So I have to do a little side work here. My z is going to be negative x squared, and my dz dx is going to be negative 2x. So now, when I come back here and I look at my equation and I think about the derivative, psi prime, I have to use the constant multiple rule, which means I'm going to start with the a. The a is a constant that's going to multiply my derivative. And if I have e to the z, then that means that the derivative is e to the z, so again, e to the negative x squared, times dz dx, so times negative 2x. So my first derivative for the function looks like this. Part C, find the second derivative of this function. So the second derivative of this function is even more interesting than the first derivative, because not only am I going to have a chain rule, I'm also going to have a product rule. So here, if you look at the first derivative, you can see I have two functions multiplied together that both contain the variable x, which means I'm going to have to separate them out into f of x and g of x so that I can use the product rule. So here, my first function I'm going to call f, so a e to the negative x squared, and my second function will be my g, which is negative 2x. Now I'm going to find each of their respective derivatives. Let's start with g prime. The derivative of negative 2x is negative 2. The derivative of a e to the negative x squared, well, that's exactly what we found when we were finding the first derivative. So we already know the answer to that. It's a e to the negative x squared times negative 2x. So now we need to do f prime times g. So remember, we're calculating the second derivative. So we have a e to the negative x squared times negative 2x times negative 2x plus f times g. So here, that's going to be plus a e to the negative x squared times negative 2. Now we can simplify out this a little bit with some of our algebra. So let's see what it looks like if we simplify. So from the first term, notice I have a negative 2x times a negative 2x. So I can combine those, and that will simplify into 4x squared. So ae to the negative x squared times 4x squared. Now here I'm going to pull the minus to the front and write this as minus 2a e to the negative x squared. I could have left the 2 at the end. That would have been perfectly fine as well. But I decided to pull it up front because a lot of times we like to group our constants in the front. But this is a good way to represent the second derivative now with all of our terms, remembering that a here is a constant. Let's take a look at another problem. Example 6. Find the derivative of f of x equals sine of x cubed times the natural log of x squared minus x plus 1. So here, we need to figure out what we're doing first in terms of the types of techniques we know about taking derivatives. I see a lot of things in this problem that are going to include the chain rule, but what I notice most of all is that I have two functions multiplied together that can be completely separated by that multiplication mark. So I'm not going to start with the chain rule. Instead, I'm going to start with the product rule, and I'm going to have to do some chain rule along the way. So here, I'm going to call the first function f. So that's going to be sine of x cubed. And then my second function is g, which is the natural log of x squared minus x plus 1. Now, in order to find the derivative of sine of x cubed, I notice that I have a composite function that's been raised to a power. So for my substitution, my z for this part is going to be sine x. So I also need dz dx. Derivative of sine is cosine. So remember, with parentheses to a power, the derivative is 3z squared, but my z is sine x. So the power come down, subtract 1 from the power, times dz dx. So times cosine of x. In order to get g prime of x, I also have to do a chain rule. For the g prime of x part, my z substitution is going to be x squared minus x plus 1. And my dz dx is then 2x minus 1. With the natural log, our shortcut said we're going to have 1 over z times dz dx. And usually what happens is that the dz dx gets multiplied into the numerator. So that means I'm going to have 2x minus 1, my dz dx, times 1 over z. But my z is x squared minus x plus 1. So I had to use a chain rule for both of these to find their respective derivatives, but within the framework of a product rule. So now, putting all of that together, I'm going to be multiplying f prime times g. So that is 3 sine of x squared times cosine of x times g, which is the natural log of x squared minus x plus 1, plus f times g. So sine of x cubed times 2x minus 1 over x squared minus x plus 1. So my derivative looks like this big, huge, long function. So even though we know how to do the product rule, oftentimes we have to use other rules within the product rule to get our final answer. As long as we're careful and methodical about the way we do it, we should be able to find the solution. Let's try one more. Find the derivative of f of x equals e to the x over x to the fifth using the product rule. Now this is in a different shape or form than the other problems we've looked at. In order to be able to use the product rule, we need two functions that are multiplied together. This has a structure of one function over another one. So if we want to use the product rule, we have to figure out a way to rewrite this so that we have two things multiplied together. So one of the things we can do algebraically is we can bring up the term from the denominator if we make that 5 negative. So if we rewrite this as e to the x times x to the negative 5, it's now in a form where we can use the product rule. So here my f will be e to the x, and my g will be x to the negative 5. The derivative of e to the x is e to the x, and the derivative of x to the negative 5 is negative 5x to the negative 6. Remember, if you subtract 1 from a negative power, it becomes more negative. So now applying our product rule, we're going to do f prime times g. So we have e to the x times x to the negative 5 plus f times g prime. So e to the x times negative 5x to the negative 6. So if we want to simplify our derivative a little bit, we can make some of those powers positive again by putting them back down in the denominator. So the first term I would probably simplify into e to the x over x to the positive 5. So I'd bring that term down by changing the power back to positive. The second term here, notice that I have a negative 5. I'm going to pull that to a front. So that's going to be minus 5e to the x. So there's my 5, there's my e to the x. And now my x to the negative 6, I'm going to put that down in the denominator and make it x to the positive 6. So now my first derivative looks like two quotients here, but we were able to find these using the product rule because we were able to bring the denominator up.